Good afternoon to all of you. In last lecture, we have start a random process. So, random process is nothing but collection of waveforms Here we have to assume that x of t is the random process. This random process is nothing but collection of waveforms, or we can say that at particular time t1, t2 up to tn, we are having random variables, that is x of t1, x of t2 and so on, x of tn. So we can say that random variable is nothing but collection of waveforms, or it is a collection of time index random variables. Or these random variables x of t1, it will give the probability density function x of t1 or x. Similarly, this second random variable, it will give the probability density function x of t2 or x up to x of tn of x. This is the probability density function for all n random variables. Here, depending on this one, we are having the stationarity. We have to see whether this random process is a stationary. So we are having the three types of stationarity. First one is the first order stationarity, where we have to consider individual probability density function, or which stationarity is nothing but when we are shifting this random process, the origin time axis, when we are shifting this time axis, time origin, your random process is invariant to this shift, then we can say that x of t is strict sense stationary random process. In first order stationarity, we can say that this individual random variable x of t1, x of t2 up to x of tn, which will give the probability density function for x of t1, x of t2 and x of tn. We are looking separately these n random variables for first order stationarity, that is your narrow sense stationarity process, where this f of x of t1 or this x at time t1 is equal to f of x t1 or x t plus delta. The probability density for your first random variable x of t1 from your random process x of t, here whatever the probability density function at this time t1 is given as this first f of x t1 of x at time t1 is remains same when we are shifting this random variable with some distance delta, some time delta. So the probability density function for shifted x of t1, that is x1 of t1, x t1 plus delta. These probability density functions are remain constant. They are remain constant. Then this process is called as first order stationary process. This process is called as first order stationary process or narrow sense stationary process. This is a true for all the random variables for t1, t2 up to tn, but individually. Then we are having the wide sense stationary process. Now we have to consider these two random variables at x of t1 and x of t2. So we are looking these two random variables at a time. We can say that these two random variables, their probability density function, that is joint probability density function, x1, x2, x1, x2 at time t1 and t2. This is the joint probability density function for these two random variables at time t1 and t2 from the same random process x of t. Or this one, when we are shifting this, when we shift these two random variables, first random variable with the distance delta, that means t1 plus delta, and second random variable is also shifted with the distance delta, then we will get this new position for this one. These two random variables are get shifted in time origin, time axis. Then we will get probability density function for x1, x2, x1, x2. Here time is get shifted t1 plus delta and t2 plus delta. The probability density function at this time is remain constant when we are shifted with some amount delta. Then joint probability density function for these two random variables x of t1 and t2, they are remain constant, then we can say that this process is nothing but wide sense stationary process. First one is narrow sense stationary process. This is the true for any two random variables from your random process. This is true with x2 and x3. Suppose this is your third random variable at time t3. At time t3. So we can see that t2 and t3, their joint probability density function, small f of x, x2, x3 or x1, x2, x3 at time t2, t3. When time is get shifted, t2 plus delta and t3 plus delta, their probability density functions are remain constant. They are invariant of time shift. Then we can say that this is a wide sense stationary process. Similarly, for all n random variables from t1 to tn, x of t1 to x of tn, for all n random variables, their joint probability density function for n random variables, that is x1, x2, x3 up to xn, x1, x2, x3 up to xn, or the time t1, t2, t3 up to tn. This is the probability density function for all the random variables present situation. Now this complete process is get shifted with some amount delta. Means every random variable that is at time t1, t2, t1 plus delta, t2 plus delta, t3 plus delta up to tn plus delta. So here when this new probability density function for x1, x2, x3 up to xn, for x1, x2, x3 up to xn, for the time t1, t1 plus delta, t2 plus delta up to tn plus delta. This complete probability density function for these n random variables, they are remain constant or invariant to this time origin shift. Then this process is called as strict sense stationarity. Strict sense stationary random process. The second statement is the statistical averages for narrow sense stationary, first order stationary process, where we have to consider individual random variable, it will give its mean value. So for this case we can say that expected value of x of t is remain constant. Expected value of x of t is remain constant, or it should be a real number. It should be a real number, constant value. Then for second case, wide sense stationarity, we can say that it should give expected value of x of t that is equal to constant, and autocorrelation function for this t2 minus t1 is equal to r of, means whatever the correlation between these two random variables x1 and x2 at time t1, x of t1 and x of t2, autocorrelation function, correlation function for these two random variables xy, for these two random variables xy, it is given as expected value of x into y. Similarly here we are having the correlation function between these two random variables x of t1 and x of t2 from the random process x of t. So here this correlation function is only depends upon this time shift. Only depends upon this time shift, that is your tau value, which is given as tau is given as t2 minus t1. Only we are depending on this difference, not exact value. What should be the value of t2? What should be the value of t1? Whatever. Only we are related with this time difference. Only we are related with this time difference. Then this is the checkpoint for your wide sense stationary process. You are given any process, random process. First of all, you have to find out where is its mean, expected value of x of t. For overall this complete random process, we have to find out its a mean value. Secondly, we have to find out its the correlation function. Whatever the correlation function, it should be a function of time difference tau. It should be a function of time difference tau. So depending on this one, we have to take one example, write down. For the random experiment of throwing a die, we will get the sample points omega, that is equal to 1, 2, 3, 4, 5 and 6 for all omega I, for all omega I, let x of t comma omega I, that is equal to omega I e raised to minus t u of t denote the random process x of t omega I, that is equal to omega I into e raised to minus t u of t is the denote the random process. Now we have to sketch the random process for this experiment. Just we are throwing a die which will give the 6 outcome, that is your omega 1, 2, 3, 4, 5, 6. Here this is your omega 1, omega 2, 3, 4, 5 and 6. This x of t gives the random process. As per the definition, random process is nothing but collection of waveforms. Collection of waveforms. So here we are having the 6th outcome. Definitely we will get the 6 waveforms. So here x of t omega 1. Try to draw the waveform for x of t comma omega 1 for first sample. First sample gives the waveform. Here omega I is nothing but 1 e raised to t u of t. So here we will get function with magnitude 1. Similarly, we are having this x of t comma omega 2. We will get the second waveform which is corresponding to omega 2, that is 2 value. Second sample. Here we will get this with this magnitude 2 exponential signal. Third one, x of t comma omega 3, where 3. X of t omega 4 with height 4, and other two sample waveforms with the height 5 and 6. Is it clear? With the height 5 and 6. So for this experiment, throwing a die, we will get 6 sample values. For these 6 sample values, we are having the 6 waveforms for the random process x of t comma omega I, which is given as omega I into e raised to minus t u of t. So over this one, we can define approximately at time t1 is equal to 1. For time t1 is equal to 1, we will get your first random variable. So here x of t is equal to 1 omega I, it will give value 1 into e raised to minus 1 u of t, then second 2 into e raised to minus 1, 3 into e raised to minus 1, 4 into e raised to minus 1, then 5 into e raised to minus 1, and lastly 6 into e raised to minus 1. Is it clear? This is your first random variable or this random process where we are having the 6 sample waveforms. At t is equal to 1, we are having the 6 sample values. That is your first 1 into e raised to minus 1, 2 into e raised to minus 1, 3 into e raised to minus 1, 4 into e raised to minus 1, 5 into e raised to minus 1, and 6 into e raised to minus 1. Similarly, we will get at t is equal to 2 omega I. This is your second random variable at time t is equal to 2, where we will get the values 1 into e raised to minus 2, then 2 into e raised to minus 2, 3 into e raised to minus 2, 4 into e raised to minus 2, 5 into e raised to minus 2, and 6 into e raised to minus 2. Up to n random variables. At t is equal to n, x of t is equal to n omega I. We will get the 6 sample values with individual probability. Here this sample is occur with the probability of 1 by 6. 1 by 6. For every sample their individual probability is 1 by 6. So for this first random variable, we have to draw its probability distribution function and probability density function. Only case is at t is equal to 1, I am standing at this point and looking upward, we will get this first value, that is 1 into e raised to minus 1 with probability of 1 by 6. Second value 1 into 2 into e raised to minus 1 with the probability of 1 by 6. So here 1 into e raised to minus 1. So this x1 omega I, we will get the values 0.3679, then 0.7357, then 1.1037, 1.5616, 1.8395 and 2.2074. These are the values of first random variable. So for this random variable, we can draw the probability distribution function, that is capital F of x for this first random variable. 0, the first value is 0.36, then 0.7, 1.1, 1.5, 1.8 and 2.2. Each one has the probability of 1 by 6. So here we will get the probability of 1 by 6. At this point, one by 3, 1 by 2, 2 by 3, 5 by 6 and 6 by 6. This is the probability distribution for the random variable x of t1 for this random process x of t. Here we can find out it's a probability density function. For this range 0.36 to 2.2, we will get equal probability, that is 1 by 6. This is a uniform distribution. Is it clear? Similarly, we can draw probability distribution function and probability density function for second random variable x of t2 comma omega I, which will give these values. Similarly, for up to t is equal to n, x of tn, each will give the same probability distribution and density functions. This is the example of random process. Is it clear to all of you? Write down next example. Consider the experiment of tossing a fair coin. Consider the experiment of tossing a fair coin. The random process is defined as follows. Consider the experiment of tossing a fair coin. The random process is defined as follows. X of t is equal to sin pi t if head occurs, and x of t is equal to 2t if tail occurs. If tail occurs, sample functions sketch the sample functions, we wish to find the expression, for probability density function of the random variables obtained from sampling the process at t is equal to 0 and t is equal to 1. T is equal to 0 and t is equal to 1. In this problem, we are tossing a coin, fair coin. Here we are having the x of t. X of t is equal to sin yt and x of t is equal to 2t. This is for head occurs and this is for tail occurs. Here sketch the sample functions. We wish to find the expression for PDF, probability density function of the random variables obtained by sampling the process at t is equal to 0 and t is equal to 1. So here for this experiment we are having the two sample values, head and tail. When head occurs we are having the sine waveform, first waveform, and tail occurs we are having 2t. So here we will get x of t is the random process which will contain the two waveforms corresponding to two sample values. When head occurs we are having the sine waveform and when tail occurs we are having 2t. Zero, 1, 2. This height is 1 minus 1. 0, 1, 2. So here x of t is a random process. From the random experiment, tossing a fair coin which will give the two outcomes, either head or tail with the probability 0.5. So here when head occurs we are having the sine of pi t. This is your first waveform for your first sample. For second sample x of t is equal to 2t for tail occurs. Here we have to find out the function, sample this one at t is equal to 0 and t is equal to 1. That means at t is equal to 0 we will get first random variable and t is equal to 1 we will get second random variable. So at t is equal to 0, in first case t is equal to 0, we will get x of t is equal to 0, comma, wi. What are the values for this random variable? Yes? 0, 0. T is equal to 0. At this time t is equal to 0. I am standing at this point and looking upward. We will get these two values 0 and 0. So for this random variable, can you draw the probability distribution function, and it's a probability density function. For this random process, at t is equal to 0, we get the random variable x of t is equal to 0 omega I. This will give the two values 0, 0 with the probability of 0.5 and 0.5. So for this random process, you have to draw the probability distribution function and probability density function. So at this 0, for this first sample value or this random variable, this is your omega I. At 0, head occurs with the probability of 1 by 2 plus tail occurs with the probability of 1 by 2. So we will get 1. Is it clear? At same sample point, we will get probability is equal to 1. Final probability is 1. And at this point, we will get impulse with height 1. So this is given as delta x. Mathematically, this probability density function can be given as delta x. At 0, we are having the impulse of height 1. Similarly, for your second random variable, for the second random variable at t is equal to 2, t is equal to 2, here t is equal to 1, sorry, for t is equal to 1, we will get this first sample value and here this sample value. So for this t is equal to 2, 1, this b, t is equal to 1, we will get x of t is equal to 1 omega I. It will take values at 0. What is the height? 1. Its derivative 1. Now for second one, at t is equal to 1, at t is equal to 1, we will get this value 2, 0. So it will take value 0 and 2. Is it clear? For this first head, this value becomes 0. For the second function, tail occurrence, this value becomes 2. Height is 2. Is it okay? With probability of 0.5. So we can draw the probability distribution function and density function for this second random variable. Here 0, 2, 1, 0, 1, 2. Here this first component 0, this one 0 is occurs with the probability of 0.5. Then second component 2, here tail occurs with the probability of 0.5. This is the probability distribution for random variable at t is equal to 1. Then we will get derivative probability density function. At 0, we will get impulse of the height 1 by 2. At 2, we will get impulse of the height 1 by 2. Is it clear? We will get the impulse of the height 1 by 2 at 0 and 2. Mathematically, we can define this as the first impulse 1 by 2 delta x plus second impulse 1 by 2 delta x minus 2. So this can be defined as second probability density function. Mathematically it can be defined as 1 by 2 in bracket delta function at t is equal to 0 plus delta function which is shifted x minus 2. Delta function at t is equal to 0, delta function at t is equal to 2 with the height 1 by 2. Is it clear to all of you? In this problem, experiment is tossing a fair coin. When we are tossing, we are having either head or tail. When head occurs, we are having the sine waveform, sine pi t. When tail occurs, we are having 2t. So over this one, we are having the two sample values, t is equal to 0 and t is equal to 1. At t is equal to 0, we will get these 2 points 0, 0. These are the values for these two samples with the probability of 0.5. So we can draw the probability distribution function. At 0, we are having 1 by 2 plus at 0, 1 by 2. So we will get 1. Its probability density function delta x. At t is equal to 0, we will get the impulse of height 1. So mathematically it can be defined as delta x. For t is equal to 1, here t is equal to 1, we will get two samples, that is here 2 and 0 with the probability of 0.5, 0.5. So at t is equal to 1, for this random process, at t is equal to 1 omega I, we will get these two components 0 and 2. We can draw the probability distribution function 0 and 2. At 0, we are having probability 1 by 2. Then at 2, we are having probability 1 by 2. So finally, this probability is 1. Then probability density function, derivative of probability distribution function at 0, 1 by 2 to 1 by 2. So mathematically it can be defined as at t is equal to 0, we are having the impulse of height 1 by 2 delta x plus 1 by 2 delta x minus 2. Is it clear? Now we have to see autocorrelation function. Write down. Autocorrelation for this random process x of t. The definition of correlation function, which is given as Rxy for these two random variables x and y, these are the two random variables, is nothing but expected value of x, y. Expected value of xy. This is your second order movement of your second order movement about your origin. So here we are having the two possibilities. Either this function is equal to 0, then we can say that these two random variables are orthogonal to each other. Their intersection point is 0. When this is equal to expected value of x into expected value of y, then we can say that these two random variables are statistically independent. When these two random variables are statistically independent, they are uncorrelated to each other. So here for these two random variables x and y, we are trying to find out the correlation between these two random variables. Similarly, for your random process, when we are talking about your wide sense stationary process, we are talking about your two random variables at any time t1 and t2. So here expected value of x of t1 and x of t2. Similarly, expected value of x square t1 and expected value of x square t2. These are the second order. These are the second order functions which will give the joint probability. Or this one, expected value of x of t1 and x of t2. This is the correlation function, which can be given as Rxx. Here first x stands for x of t1, second x stands for x of t2. We have to consider two random variables, or t1 comma t2, which can be given as expected value of x of t1 into x of t2. That is nothing but integration from minus infinity to infinity your x1 x2 into probability for x1 x2 at time t1 t2. Expected value or this x of t1 into x of t2 jointly, it will give the joint probability density function. Joint probability density function p of x comma x2 or the time t1 comma t2 or these two random variables, their multiplication x1 into x2. This is the correlation function for this random process. For strict sense stationary random process, we have to consider that these random variables, their probability density functions or correlation function is depends on only the time difference. So here when we consider this tau is equal to t2 minus t1, t2 minus t1. So over this rxx is given as x of t comma x of t plus tau. It is true for any two random variables from your random process. X of t plus x of t plus tau. Tau is nothing but difference between these two random variables. Distance in time domain, distance between these two random variables. So r of tau, that is equal to r of tau. And here this autocorrelation, which is a function of time difference tau, that is nothing but rx of t2 minus t1. This is the autocorrelation function. So write down the properties of autocorrelation function. First property, autocorrelation function is even function. Properties of autocorrelation function. Autocorrelation function is the even function, that is autocorrelation for this random process x, tau is equal to rx of minus 2. Autocorrelation function is even function. Then second one, mean square value of the process, may be obtained by putting tau is equal to 0. Mean square value of the process, random process, may be obtained by putting tau is equal to 0. So here for second property, rx of tau, it is nothing but expected value of x of t into x of t plus 2. Autocorrelation function, this is a general definition for autocorrelation function. This is called as autocorrelation function x because we are taking the correlation between same random variables which are just shifted with tau difference. Any two random variables. So here autocorrelation function at tau is equal to 0, that is rx 0, that is equal to expected value of x of t into expected value of t. So it will give expected value of x square of t. Is it clear? At tau is equal to 0, we will get mean square value of the process, x square of t, mean square value of the process. So this autocorrelation function here, autocorrelation, it depends upon your time reference to so tau, it is the even function. That means across this vertical axis we will get symmetry. At tau is equal to 0, at this point tau is equal to 0, we will get mean square value for the random process. Mean square value, expected value of x square t. So at here we will get expected value of x square of t. This is the autocorrelation function which obeys these two properties. First property, even function, we will get symmetry along the vertical axis, and at tau is equal to 0, we will get mean square value for your random process x of t. For your random process x of t. Then for third property, Rx of tau, that is autocorrelation function, has maximum magnitude at tau is equal to 0. So here we will get, for this third property, Rx of tau is less than or equal to Rx of 0. So whatever the values, Rx of tau is equal to 1, tau is equal to minus 1. These values are always less than Rx of tau is equal to 0. So this is the maximum value for your autocorrelation function. This is the maximum value for your autocorrelation function. So here we are in the two waveforms. First one is slowly fluctuating random process. Slowly fluctuating random process, and second one is rapidly fluctuating random process. So here, for any two random variables, rapidly fluctuating random process where tau is very much smaller. Random process which is having the multiple waveforms, where we have to consider this random variable at t time, and we have to consider this random variable at t plus tau. This is the difference. Are you get it? The difference between these two random variables. First is at t, second one is at t plus tau. The difference between them is tau. As we are increasing this tau value, we will get slowly fluctuating random process. When we are decreasing this tau value, that means for first case we are decreasing this tau value. Suppose here the time difference between these two random variables becomes 0. For this case, these two random variables at same time. So our tau is equal to 0, we will get maximum value, mean square value for your random process. As we are increasing this tau value, for the same tau value, we will get this graph. This graph indicates that your process, random process, is fluctuating more faster, rapidly. When graph is first graph, then we can say that tau value, time difference between two random variables, is larger. As we are increasing this tau value, this graph is slowly fluctuating, its frequency is smaller. So autocorrelation, this is the third property. So write down, more rapidly x of t more rapidly random process x of t changes with time, then more rapidly autocorrelation decreases, more rapidly autocorrelation decreases from maximum Rx of 0 as tau increases.